in this lecture, we'll be discussing about induced EMF by the change of area in the coil, right? So we'll be starting with the induced EMF by changing the area of a coil. Then we'll be discussing about the motional EMF and self-inductance as well. So here in this section, you can see that there's a diagram where we have a rail of conductors like this, and there is this conductor of resistance. Let's suppose the resistance of this conductor here is R, right? And we have a rod of length L, and this rod of length L is sliding towards right on this rail, right? And the uniform magnetic field is mentioned here into the plane of this paper, right? P is a uniform magnetic field, right? P here is uniform magnetic field. So B is the uniform magnetic field. The length of this rod is L, right? And it's moving towards the right with the speed of V. V is the speed of the velocity of this rod towards the right. We have to find the EMF induced. First of all, we'll try to learn why actually the EMF will be induced in this rail or in this coil, right? You can see here that initially the coil was here, right? This was the position of a coil with respect to this rail. Let's suppose this coil was initially at a distance of x, right? At a distance of x from this point, right? From this point P, the horizontal distance of this rod from this resistor is x, right? And the length of this rod is L. So if we try to find the area of this rectangular portion, the area of this rectangular portion is nothing, it's L multiplied by the x, right? And we know that by Faraday's law that we can the EMF will be induced in a conductor if the flux change through the conductor, right? If the flux change through the conductor, then the EMF will be induced, right? So our EMF induced was nothing, it was equal to E is equal to minus d5 over dt, right? Now the question is how we can change the flux. Flux is nothing, it's PA cos of theta, right? BA cos of theta. So we could change the flux by changing the magnetic field intensity, or we can change the flux by changing the orientation of magnetic field with respect to area vector, right? We can also change the flux by changing the area, right? By changing the area. So this is what we have to understand, right? By changing the area. By changing the area of a coil, right? So initially this was the area of this coil, right? This is the area of this coil, right? And this is the length of this coil, that's L, and X is the distance from this point. Now as this rod moves towards the right, the X actually increases. The value of X increases, or we can say if X increases, the length of this rod is a constant, the area of this coil actually increases or area changes, right? Area change. If the area of this coil changes, it means that the flux linked with this coil will change, right? Flux linked with this coil will change. If the flux linked with this coil changes, then the EMF will be definitely induced in this circuit, right? So that EMF we have to calculate, right? That EMF we have to calculate. Now flux at any time t will be equal to, that will be P times A cos of theta, right? Cos of theta. And you can see that magnetic field vector, right? Magnetic field vector and the area vector are parallel to each other, or we can say the angle between them is 0 degree, right? 0 degree, or the flux at any time t will be equal to P into A. This will be the flux at any time t, right? B is the uniform magnetic field. And area is given by B times, that's P into area is L into X. We will multiply here with L into X. And this X is now a variable because this X is continuously changing because it's a horizontal distance of this rod from this point, let's suppose P, right? From this point P, and it is continuously changing because of the speed of this rod along the horizontal direction, right? Now, if we take the derivative here, that's d5 over dt, right? d5 over dt, that will be equal to P times L dx over dt, right? Dx over dt. And this dx over dt is nothing, it's the rate of change of this horizontal distance with respect to time. That's nothing, that's the speed or the velocity of this rod, right? So we can replace this dx over dt with V. So the EMF induced will be d5 over dt, right? Or we can say that modulus of this EMF induced is nothing. It's actually equal to PL into V, right? So this is the EMF induced in this section, right? So in this coil, the EMF induced will be actually given by BLV, where V is the speed of rod, right? V is the speed of rod. V is the speed of rod. If this is the EMF induced, then the current through the system will be, let's suppose R is the total resistance of the circuit. Let's suppose R is the resistance, right? And the current through this circuit will be nothing. It will be BLV upon R. So this will be the current, right? If this is the current through the circuit, BLV upon R will be the current through the circuit, right? This is the current through the circuit, right? And one more point is that the power or the energy dissipated through the circuit because of this resistance R will be given by power will be equal to I square multiplied by this resistance R, right? I square multiplied by this resistance R. And I square is nothing. I is given as PLV upon R. We can write it as P square L square P square upon R square multiplied by this resistance R, right? The power dissipated will be equal to P square L square P square upon R. So this will be the power dissipated through this circuit. And one more important point is that because of the induced current, that's BLV upon R, this induced current will also produce its own magnetic field, right? We know that conductors, when the current flow through the conductors, the magnetic field will be produced by the conductor, right? Magnetic field will also be produced by this conductor, correct? If the magnetic field is produced by this conductor, right, on this rail, then because of the magnetic field, there is also the external magnetic field. There will be a magnetic force on this conductor, right? Magnetic force on this conductor. And the magnetic force on this conductor will be given by, that will be equal to P into I into L, right? P into I into L will be the magnetic force on this conductor. And this magnetic force on this conductor will always try to reduce the flux through this area, right? We know that by Lenz's law, the induced EMF always opposes the change. What is that change? The change is anything which causes the change in the magnetic flux, right? So if the velocity of this rod towards the right tries to increase the magnetic flux, tries to change the magnetic flux, then this force on this rod will try to reduce the magnetic flux through this coil. So it means that the direction of this force has to be towards left, right? If the velocity of this rod is towards the right, then the direction of this force has to be towards the left, so as to reduce the flux changing through this area, right? So the direction of this force has to be towards left, right? It means that there will be a retardation in this coil, right? There will be a retardation in this coil. Or we can say, if we want to move this rod with some constant velocity, if we want to move this rod with a constant velocity, right, we have to apply the same amount of force on this rod towards the right, so that the rod continues to move with the same speeds or same velocity, because there is a magnetic force on this rod that's towards the left, and to maintain the speed we have to apply the same amount of force towards the right also, right? So the magnetic force Fm will be equal to PIL, and B is the magnetic field, that's B is the external magnetic field, that's P, right? And the current is actually here, that's BLV upon R, so it will be PLV upon R multiplied the length L, right? So we can write it at B square L square P upon R. So this is the magnetic force acting on this rod towards the left, right? And this magnetic force will try to reduce the flux through this rod, through this area, right? So in order to move this rod with a constant speed, we have to apply the same amount of force, that's P square L square V upon R to the right, so that the speed of this rod on this rail is maintained, right? So this was the discussion about the induced EMF by changing the area of the coil. So what we can do is that we can set up a rail like this, and on this rail we can put a rod and try to move this rod right towards the right or left. Then accordingly the EMF will be induced. Now if in case the rod moves towards the left direction, right? If the rod moves towards the left direction, then the magnetic force due to the induced EMF on this rod will be towards the right direction, right? In that case, the direction of the magnetic force will change, and the sense of the induced current will also change, right? Sense of the induced current will also change, correct? Now the question is that what will be the direction of the current? What will be the direction of the current? Now this is the loop, right? The flux is in the downward direction, right? The flux is into the plane of this paper, and this flux is continuously increasing, right? This flux is continuously increasing. Now the induced EMF will try to reduce the flux. In order to reduce the flux, the current has to be in a anti-clockwise direction. If the current has to be in an anti-clockwise direction, then we can say by the right hand rule, the direction of the magnetic field will be out of the plane of this paper. The direction of the magnetic field will be out of the plane of this paper, right? So in that case, the flux will be reduced. Flux will be reduced. So this will be the direction of the induced EMF or induced current in the circuit. Now let's try to discuss the concept of motional EMF from the Lorentz force, right? Now we'll try to uh, understand the concept of induced EMF with the help of a force, right? That's the Lorentz force. You can see in this diagram, there's a uniform magnetic field B, which is out of the plane of this paper, right? B is the magnitude of this magnetic field, right? And you can see the velocity of this rod. The rod is moving in this magnetic field region or in this field region with velocity V, right? And the length of this conductor, let's suppose, is L, right? And we know that any conductor or any material consists of a electron, right? Or particularly the conductors consist of free electrons, right? Now, if the rod starts to move, then these charges are also moving, and because of the charge moving in this conductor, right? Moving charge, conductor is moving, the charges are also moving. So because of that, we know that whenever a charge moves in presence of external magnetic field, the magnetic force acts on them, right? In the same way, there will be a magnetic force on these electrons present in this conductor, right? You can see if this is the direction of the magnetic field, then the direction of the magnetic force on these electrons will be given by the direction of the V cross B cross product, right? So if we do the V cross B, then V cross B will be directed along this direction, right? Along this direction. This is the direction of the V cross B vector, right? This is the direction of the V cross B vector. But we know that this is the direction of the magnetic force on a positive charge. But here the magnetic force is on negative charge. It means the magnetic force on this electron has to be along this direction. So this will be the direction of the magnetic force on this electron, right? So this will be the direction of the magnetic force on this electron. And what will happen is that these electrons will start accumulating on this end of this conductor, and this conductor will become positive end of this conductor because of the deficiency or deficit of the negative charge, right? So this end will attain a negative charge, and this end will attain a net positive charge, right? So this at this end of this conductor, the electrons will be residing, and at the end P, the positive charge will be there, right? So what's going to happen is that because of this two poles developed here, positive pole and the negative pole at the ends of the conductor, right? The electrostatic field will get set up, right? There will be electric field also that will be that will be directed along from positive end to the negative end, right? The electric field will be along the direction of from positive end to the negative end, right? It will be towards this Q point, right? From P to Q, there will be an electric field. It means that so more and more electrons get accumulated at the negative end, more and more electric field will be developed. It means the intensity of electric field will also increase, right? And that electric field will be opposite in direction, right? That electric field will be in opposite direction to that of the magnetic field. So there will be a time, or there will be a point when the magnetic field will be actually balancing the electric field developed across the ends of this conductor, right? Electric field developed across the ends of this current conductor, or we can say that the electric field here will be nothing. It will be equal to minus E times, right? E times V cross B, right? E cross B. V cross B. So this will be the direction of the electrostatic field or electric field here in this conductor, right? So this will be the direction of the electric field, and it will be balanced by the magnetic field, right? So E vector will be equal to actually minus magnetic field vector, right? So magnetic force vector, right? Now the potential difference will be developed across the two ends of the conductor because of the motion of these charged electrons, charged particles, right? Because of these electrons, the EMF or the potential difference will be developed because of the motion of this rod. The force acts on the electrons present in the rod, and EMF get developed across the two ends. So that's what we call as motional EMF from Lorentz force. Motional EMF from Lorentz force. So EMF will be developed, right? The EMF developed across the conductor, right? Across the conductor, that's given by, that will be integral of, that will be equal to integral of V cross B dot dl, right? V cross B dot dl. So this will be the EMF developed across the two ends of a conductor, right? It will be V cross B dot dl. So this is the EMF developed across the ends of a conductor, right? Of a conductor due to Lorentz force. So EMF will be developed across the ends of a conductor because of this Lorentz force, right? Now the question is that what will be the direction, which end of this rod will be at high potential and which end will be at the low potential. You can see that V cross B is directed along this direction, right? V cross B is directed along this direction, and this end of this rod will be at higher potential. That will be HP. That's higher potential, right? Higher potential. And this end will be actually at lower potential. Or we can say higher potential end will be given by V cross B vector, right? V cross B vector. So V cross B vector will give us information about which end is going to be a higher potential end, which end will be the lower potential end for a conductor, right? Which is moving in presence of an external magnetic field, right? In presence of an external magnetic field. So integral of V cross B dot dl will be the EMF developed across this conductor, right? Now let's suppose that we have a conductor. Let's suppose that the magnetic field is directed along this direction, right? Magnetic field is directed along this direction. This is the direction of the magnetic field, right? This is the direction of magnetic field. And in this region, we have this conductor or a rod of length L, a rod of length L, and this rod is actually moving along this direction with speed v, right? With speed v. So we have to find the magnetic EMF or EMF developed in this rod, right? We have to find the EMF developed in this rod or the potential difference across the two ends of this rod. You can see that the velocity vector is actually along the direction of this magnetic field vector. If velocity vector is along the direction of the magnetic field vector, then V cross B in this case will be equal to 0, right? If V cross B is 0, it means that EMF produced or the developed across the two ends of this conductor will be equal to 0. So whether EMF will be developed in the conductor or not, it also depends upon the orientation of velocity vector with respect to the magnetic field vector, right? Because we know that the force acting on a charge in a conductor which is moving in presence of external magnetic field depends upon the orientation of velocity vector and magnetic field vector as well, right? So V cross B will give us the information whether there will be a magnetic force on a conductor or not, right? If there is a magnetic force on a conductor, then definitely there will be EMF developed across the two ends of a conductor, right? Now let's try to solve this question here, right? Let's try to find the EMF developed across this rod, right? You can see here a rod PQ of length L moves with a uniform velocity V parallel to a long straight wire, right? Parallel to a long straight wire. It's a infinite straight wire, right? Carrying a current I, the end P remaining at a distance R from the wire, right? So P end has been given that it's given that the end P is at a distance of the end P is at a distance of R, right? End P is at a distance of R. And this rod is actually moving in the upward direction with velocity V, right? The velocity of this rod is V in the upward direction, right? This is the velocity V, correct? And we have to find the induced EMF, calculate the EMF induced across the ends. So we have to calculate the induced EMF across two ends, end P and end Q of this conductor, right? And this conductor is moving in upward direction with the speed of 5 meters per second, right? Correct. And the current I is equal to 100 amperes, right? You can see that how actually the flux linked through this, or we can say how actually the EMF will be developed through this conductor, right? You can see that this conductor is moving, right? If we try to calculate the direction of the magnetic field vector with respect to this velocity vector, and we know for because of the infinite rod, the direction of this magnetic field at this point will be in the downward direction, right? It will be in the downward direction, right? If this is along the downward direction, if this is along the downward direction, then the velocity vector is perpendicular to this magnetic field vector. It means that the magnitude of the EMF will be maximum here, right? Or we can say that V cross B will be equal to V into B, right? V into B. Now we can see that we can see here that let's suppose this is Tx vector, or we can say that V cross B vector will be actually along this DL vector, right? It will be actually along this DL vector such that integral of V cross B dot DL, V cross B dot DL, right? We can write it as, since V cross B vector is along the direction of this DL vector, we can write it as VBDL. We can write it as VBDL. So this will be the integral, or this is how we can calculate the EMF because of this, right? Now we know that at each and every point, or at a distance of x, right? At a distance of x from this wire of carrying current I, the magnetic field at different points is different. It means that magnetic field is not a constant magnetic field here. It's a variable magnetic field here, right? And we know because of the magnetic field, because of the infinite current carrying conductor is nothing. It's equal to mu naught I times upon 2 pi times the distance of the point from this conductor. Let's suppose it's at a distance of x. We have taken an element dx, right, at a distance of x. So the magnetic field here at this point will be mu naught I upon 2 pi x, right? So we'll substitute the value of this magnetic field in this equation. So E will be nothing. It will be integral of V times B is mu naught I upon 2 pi x, right? Mu naught I upon 2 pi x. And dl we can replace with this dx, right? Dx. Now we have to calculate the EMF induced between the two ends. That's from P to Q, right? So we have to integrate this equation from this point to this point, right? And this is the reference line. This is the reference line, right? So this point is at a distance of R, right? And if the length of this conductor is L, then this point will be at a position of R plus L. So we'll integrate it from R to R plus L, right? R to R plus L. So it will be mu naught I V, right, upon 2 pi integral of dx upon x with limits R to R plus L. And the integration of dx over x, integration of 1 over x with respect to x is nothing. It's log of x, right? So we can write it as mu naught I upon V upon 2 pi log of x, right, with limits R to R plus L, right? R to R plus L. So EMF induced here will be mu naught I V upon 2 pi, right? So it will be ln mod of R plus L upon R. So this will be the EMF induced across the two ends of a conductor, right? Now we can substitute the value of V, L, and R in this equation to get the value of EMF induced across two ends of the conductor. Now, how can we know which end is at higher potential and which end is at the lower potential? What we can do is that we can simply uh, find the direction of the V cross P, right? The direction of the V cross P is actually along this direction. So this is the direction of V cross P. It means that this end will be at higher potential, right? This end will be higher potential and this end will be a lower potential, right? This will be a lower potential end. So P end will be the higher potential end and Q end will be the lower potential end. Now, similarly, we have to find the induced EMF due to rotation of a conducting rod in a uniform magnetic field. Once again, we will be using the same equation. We can use the same concept that it's a motional concept of motional EMF induced will be integral of V cross P dot dl, V cross P dot dl, right? V cross P dot dl vector. Now you can see this rod is moving in a circular area, right? Let's suppose this circle is of radius r, right? In a this rod is moving in a circle about this point O with the angular velocity given as omega. Omega is the angular velocity, right? Now omega is the angular velocity. We know that whenever an object moves in a rotational motion, right? For example, for this rod is moving in a rotational motion, then each and every point for this rod has the same angular velocity, right? Each and every point on this rod has the same angular velocity. But the question is that, every point on this rod is not having the same linear velocity, right? Every point on this rod is not having the same linear velocity. The velocity of each and every point on this rod is actually different. Omega is same, but the velocity is different. So velocity of every point on this rod will be at a distance of x, that will be given as v is equal to x times omega, right? X times omega. So let's take this element dx at a distance of x from the center, right? Then the EMF induced because of this will be v cross p dot dl, right? So v cross p will be along this dl vector, or we can write this E induced vb dx, right? Integral of vb dx, and v here is nothing, that's equal to x times omega, right? That's x times omega, so it will be integral of we can replace v with x omega, right? V is a constant here, dx, right? Now we have to calculate the EMF induced in this rod rotating with angular velocity omega. So we have to calculate the EMF between two ends O and P, right? O and P. Now this O is at a reference of 0, it means it's at the origin, right? And this P is at this end, so its position will be equal to R. So we have to integrate it from 0 to R, right? So it will be omega B. Integrating x with respect to x will be x square over 2, right? With the limits 0 to R, right? The EMF induced will be nothing. It will be B omega R square over 2. So this is the induced EMF across the two ends of uh, conductor, right? Across the two ends of a conductor, which is moving in this circular path, right? With the angular velocity of omega, right? The angular velocity of omega. Now, if suppose we have to calculate the potential difference or the EMF between the midpoint of this rod, right? Midpoint of this rod uh, and this end, right? Let's suppose this is the Q is the midpoint of this rod and P is the end of this rod. So between midpoint and P, we have to calculate the EMF. So what we can do is that we have to just change the limit, right? We have to change the limit. We have to integrate it now from Q to P only, right? To calculate the potential difference between the points Q and P, right? In that case, we can write here between Q and P, potential difference will be potential difference will be so this E will be actually integral of the same x omega b dx, right? But now the limits will change. Now the limits will be from R by 2 to R, right? R by 2 to R. So it will be P omega x square over 2. The limits R over 2 to R. So it will be B times omega upon 2. It will be R square minus R square upon 4, right? R square upon 4. Or it will be nothing. It will be equal to, so it will be 3R square upon 8, or we can write it as 3 upon 8 P omega R square. So this will be the induced EMF between the two ends, or between the center and end of the rod, right? Now let's move to another topic. It's a very important topic, and the topic is self-induction, right? Concept of the self-induction. Right, you know that whenever through a coil or a conductor, the EMF is induced whenever there is a change in magnetic flux, whenever the magnetic flux is changed, right? EMF is induced in a conductor, right? In the same way, let's suppose this is the circuit here and it's connected to connected to this current source, right? This is a current source, right? And the resistance R is connected with it, and there is a coil, right? And we know that whenever current flows through this circuit, there will be magnetic field associated with this coil, right? And this is the direction of the magnetic field. Now the question is that how we can actually induce the EMF in this coil, right? Because of its own current, because of its own change in the current, right? So we can, if current source can be changed, if we have a variable current source, it means that if we can change the uh, current continuously, then if the current flowing through this circuit is changed, then the magnetic field will change. And the magnetic field, you can see that magnetic field is linked with the circuit, linked through these coils. If the magnetic field is changed, then the flux linked to these coils will also change, right? And that change in the flux through this system will lead to the induction of the EMF, right? Will lead to the induction of the EMF, right? Or we can say that here we have actually changed the flux in this coil because of the change of its change in its own current, right? Change in its own current, and the EMF gets induced in this coil only, right? So you can see that we can change the EMF, we can change the current by we can change the magnetic field by changing the current, and the magnetic flux also changes. So the EMF gets induced in its own coil, right? So because of the change of its own current, so that's what we call as the self-induction, right? Self-induction. So this is the phenomena of a self-induction, right? And this induction, because of that induction, the magnetic field changes. Now the sense of that induced EMF will be like that induced EMF will always try to oppose this change in the magnetic flux through it, right? If the current is reduced in the circuit, it means the magnetic field is reduced, or the change in the magnetic flux is a negative change, right? Then EMF will be in such a way induced so that the flux through this coil increases, right? And vice versa, right? So this is how we can change the magnetic flux through its own coil, and the induction EMF will be induced. That's what we call as self-induction, right? And the change or the opposition of this coil, right? Change or the opposition of this coil to change in its own magnetic flux is actually measured by a quantity what we call as self-induction of a coil, right? It's measured by a quantity. That opposition is actually measured by a quantity what we call as self-inductance of a coil, right? Now let's suppose if the current through the coil is constant. If the current is constant, it means that if current is constant, P will not change. P is not going to change, right? P will not change. If P will not change, flux will not change. There will be no induced EMF, right? B will not change. Or we can say EMF induced will be equal to zero, right? EMF induced will be equal to zero, right? But the question is that the flux will be associated, still linked with this coil, right? Flux will be still linked with this coil, and the flux linked to this whole conductor will depend upon the number of turns in this coil also, right? And the current flowing through this circuit, right? So or we can say that if n times phi is the flux through this conductor, right? So it will be directly proportional to the current flowing through this circuit, right? Current flowing through this circuit, right? We can replace this proportionality with a constant, that's L, and this L we call as inductance of a coil, right? This L is what we call as inductance of a coil. Inductance of a coil. In this first case, since flux is not changing, the EMF induced will be equal to 0. There will be no EMF induced. So this L will be nothing. It will be N phi upon I. So this will be the inductance of a coil, right? And this inductance is actually a property of this inductor, right? Property of this conductor, right? And it is independent independent of the amount of current flowing through it. Because if we increase the current, then the phi is also increasing, so that there will be no change in the L. So L will still be a constant, right? So it's actually a property of this conductor also, right? Now the say case second is that a current through the coil changes. Now the question is that what will happen if the current through the coil changes? We know that when current through the coil changes, then the flux linked with the coil is going to change. Flux linked with the coil will change. If the flux linked with the coil changes, then the EMF will be induced in the coil. There will be EMF induced inside the coil. And we have to calculate how much EMF will actually be induced in the coil, right? So you can see here case second, current through the coil changes with respect to time, right? So we know that n phi is equal to L times I, right? And L times I. So the current change, so flux also change. So we can take the derivative of this equation on both sides. If we take the derivative of this equation on both sides, that's n times d phi over dt will be equal to L times di over dt, right? Di over dt, correct? L times di over dt. We know EMF according to the Faraday's law, that's nothing. That's minus d phi over dt, right? That's minus d phi over dt. This is the induced EMF, right? This is the induced EMF. So we can, if we multiply this equation with a negative sign on both sides, so this minus n d phi over dt will be the total EMF in this conductor. So we can replace this by E now. So it will be the total EMF in this conductor, or we can say self-inductance, or the EMF induced because of the self-inductance, is actually given by a minus L di by dt, right? So this will be the EMF induced in that conductor. So minus L di by dt will be the EMF induced in the conductor, or we can say the current through this conductor will be actually EMF induced over the resistance at any time t, right? So this is the EMF induced in this conductor, right? Now question is that how we can calculate the value of this L, right? It actually depends upon the geometry of a conductor as well, right? You can see how it actually depends on the geometry of a conductor. You can see that our L was actually equal to, it was equal to N times phi over I. This was the equation of calculation for self-inductance, right? We have to calculate the self-inductance of a solenoid, right? We know that, let's suppose if the self-inductance is in a solenoid, right? If we induce the EMF in a solenoid, and we know the magnetic field inside a solenoid is nothing, it's mu naught times Ni, right? Mu naught times Ni. We can change the current in the solenoid. If the current changes, then the EMF will be induced in this solenoid, right? Now, B is equal to mu naught Ni, right? So the flux through the solenoid will be equal to phi. That's equal to phi will be equal to the area of this coil, right? That will be B into A, right? That will be mu naught. Let's suppose N is the number of turns per unit length. If the length of this solenoid is L, then we can replace this N by N upon capital L, right? N upon capital L into I multiplied by A, right? This is the flux through this solenoid, right? Now replacing this phi in this equation, we get the value of L, or this coefficient of self-inductance, as N times phi. Phi is mu naught N I A, right? Upon the length of this conductor, right? Now this we can replace this length by small l to differentiate it. So this is by small l, right? And this current I, right? This current I. Now this I and I will get cancelled, right? We'll be left with mu naught N square A upon L. I can see here it actually directly depends upon the geometry of a conductor, right? It depends upon the geometry of a conductor. It does not depend upon the current flowing through the conductor. So the coefficient of self-inductance is actually independent of the current flowing through it. It only depends upon the geometry of a conductor, right? So this is how we can calculate the self-inductance of a solenoid, right? That's mu naught n square A upon L, where n is the number of turns, right? You can write here n is nothing, it's number of turns. Number of turns. And small l is nothing, length of solenoid. Just length of a solenoid, right? And A is nothing, it's the area of cross section, right? Area of cross section. So this is how we can calculate the value of L, right? Now you can see here we have questioned the current in a solenoid of 240 turns having a length of 12 centimeter and a radius of 2 centimeter. Change at the rate of 0.8 amperes per second. Find the EMF induced in it, right? We have to find the induced EMF in it, right? So induced EMF nothing. Induced EMF is actually equal to minus L times TI over TT, right? TI over TT. The value of TI over dt is given as, it's the rate of change of this current, right? That's TI over dt. That's given as 0.8 ampere per second, right? 0.8 ampere per second. Now we have to calculate the value of L, right? For a solenoid, the value of L was equal to mu naught n square A upon L. That's mu naught n square A upon L, right? A upon L. The value of mu naught is nothing. It's 4 pi times 10 to the power minus 7, right? We can substitute the value of mu naught here. This is a small l here. That's the length of this conductor. So L will be 4 pi times 10 to the power minus 7. And the value of n is 240. It will be 240 square. Now the area of this circular portion will be pi r square, right? The radius is given as 2 centimeters. So it will be pi r square. It will be 2 over 100 cos square, right? Upon the length of this solenoid. The length of the solenoid is 12 centimeter, or we can write it as 12 upon 100. So from here you can calculate the value of the L, that's self-inductance, right? Self-inductance. Now substituting the value of L or the self-inductance into this equation, right? Into this equation directly, we'll get the value of EMF, right? We get the value of EMF induced inside this solenoid. So this will be the self-induction. This will be the self-induction for this solenoid, right? And similarly, we can have a mutual inductance as well, right? We can have a mutual inductance as well. You can see that we have two circuits here in this diagram. One circuit we call as a primary circuit, right? And another we call as secondary circuit, right? Or the second primary coil or the secondary coil. So mutual inductance is you can understand by the definition itself, right? It's the induction of the EMF because of the other circuit, right? Or the other coil, right? So it's a mutual induction. It means that the magnetic field linked because of this primary circuit to the secondary coil is changing, right? Similarly, magnetic field linked with this primary circuit because of the secondary coil is also changing simultaneously. It means that they're inducing EMF to each other mutually. That's what we call as mutual induction, right? So this is the concept of the mutual induction. So there are two coils here. One is the primary coil, another is the secondary coil, right? Primary coil and secondary coil. Let's suppose N1 turns are there in the primary coil and phi1 is the flux linked with this primary coil, right? And B1 is the magnetic field through it, right? And L1 is the coefficient of self-inductance, right? Similarly, N2 is the number of turns in secondary, phi2 is the flux through this secondary coil, and B2 is the magnetic field of the secondary coil, right? And L2 is the coefficient of self-inductance for secondary coil, right? So the flux linked with this primary will be nothing. It will be N1 times phi1, right? N1 times phi1, correct? N1 times phi1. And this flux through secondary will depend upon the magnetic field in the flux through the primary will depend upon the magnetic field change because of the secondary, right? We can change the flux through the primary by changing the current in the secondary coil, right? So it means that N1 phi1 will be proportional to the current I2, that is the current flowing through the secondary coil, right? That is the current flowing through the secondary coil. So this proportionality will be replaced with a constant, right? That is M, and this M is nothing. This is what we call as coefficient of mutual inductance. Coefficient of mutual inductance. Coefficient of mutual inductance. This is nothing. It's the coefficient of mutual inductance. Or we can write this M as M is equal to N1 by 1 upon I2, right? Right. So this is the concept of the mutual inductance. So the concept of mutual inductance is actually that we can induce EMF in the second coil because of some change in the first coil, right? So in the secondary coil, if we change the current in the secondary coil, right? Let's suppose this is a solenoid, right? If this is a solenoid, we know the magnetic field because of the solenoid is nothing, it's mu naught Ni. Or we can say that the magnetic field in the solenoid is proportional to the current through it, right? So if I is changed, or if we increase the I, then the flux linked to this coil will also increase, or the flux will change. If the flux will change, it will change because of the current changed in I2, right, or the secondary coil. And because of that, EMF will be induced in the primary coil. And that EMF will actually oppose the change in flux in the primary coil, right? So this is how we understand with the mutual inductance. We'll be deriving the equation for the EMF for the mutual induction, right? And we'll be also deriving an equation for the effective or the relation between the mutual inductance and the self inductance, right? That we'll be doing in the next lecture. We'll stop here. Till then, take care and goodbye.